Okay, thank you. I think this is working. Let me. Can hear. You see difference or? Okay. Oh. So, okay. So let us see where we were. So we were in this class of problems, and we came to the problem of gaps. This is a phenomena. Of course, this is the incompleteness phenomenon of this quotient structure, and it should be, if you are studying quotient structure, you will see that this particular one will be likely to be relevant. So a gap there is usually thought as a gap of two families, although we are going to go higher to higher dimensions. The phenomenon was first discovered by Hausdorff, his well-known omega-1 gaps. There are also analogies between omega-1 and omega-1 gaps and Arnstein trees. Somehow, construction was very early, even earlier than Arnstein is early 20th century, reproved again or republished again in 30s. But here we'll study it. I'll remind you what exact results were. So we have this notion of almost disjointness, orthogonality. I should perhaps point out that a similar, it makes sense to looking at other context of this theory of gaps, where they're not just a family of orthogonal families of sets, but orthogonal families, say, of measures or something like of that sort. Anyways, this is a notation just to fix that. And okay, gaps of preideals. Typically, you have two orthogonal families. If they are orthogonal, meaning that every element of A is homogeneous with element B, you can close off under finite union, and you are still keeping this property. Since the families of these finite unions will form ideal. It turned out actually, and that's how originally one usually thinks about the gaps of ideals and their preideals. But when you study descriptive combinatorics context, preideals are better because you're avoiding the difficulties recognizing difference between Borel and pi 1, 1. So in other words, for general preideals are better suited. And also, one thing you should keep in mind that the preideal, what is a preideal? Is an open subset of a beta n, or if you like, open subset of beta n minus n. It's a not regular open set. Ideals are typically regular open sets. This is simply open set. Okay, so you have a sequence of such with indexed by a finite set. Recently, we started actually to look at the infinite sequences of this. Also, there seems to be a theory there. But anyway, let's look at the separated means that you can dominate all of them with a disjoint intersection. When you have two of them, set and its complement would do, and it's two. But here is a. Well, I mean, if you're thinking in the terms of open spaces, this simply tells you there is a point in the boundary of the intersection. There's a point in the intersection of boundaries. This is exactly this point in the intersection of boundaries. And you take a family of subsets. You will see in a moment. Perhaps it's very unnatural. I said, why do you care about this? So in other words, you like to see that if you take the members from xi from gamma I, they should have a finite intersection. So there, of course, there are two cases. The most, this is just every pair have a finite intersection. This orthogonality, but it turned out that actually for in application you need arbitrary access. As a matter of fact, in the original where this was discovered, lower bound for the norms of averaging operators, which is essentially simply another way of saying you have a compact space, you have a continuous onto map onto another compact that you like to reverse map, and you like to make it as continuous as possible, and which you can of course measure, and which means you need to have a good selection, and that the existence of the very complicated existence x, the power set of x, will tell you that the norm is at least log of n. So that's how really it was discovered. So there are these two cases. If you're interested in the classification problem of this, the n star gaps are the atoms. In other words, the union of them would get you every gap. So in other words, there's somehow two extreme cases. As I said, first case is the most natural. Everybody can think about this. The second one is actually the one if you want to classify it. You'll see. I'll perhaps give you some examples. And this is that very well known fact where Aleph1 shows up, like in the case of the Einstein. In a Countryman line is some statement. It says the linear order set whose square is union count many chains. There's no other canality than Aleph1. There's no. So Aleph1 shows up here also, even though the structure is highly set theoretical, meaning that almost all invariants can be pushed away from Aleph1. But this one cannot. And there is a difference between, I mentioned this, there's a difference between k equal 2 and a bigger k. See, Martin actually will not do anything to the Hausdorff gap, but it can do something if k is bigger than 2. So difference. And so a Hausdorff gap is of course, there was a Rusin and Hausdorff constructing two different kind of a gap, actually, using, of course, same idea, which is Hausdorff's idea. But if the sizes are symmetric on almost inclusion, then you will call it a Hausdorff gap. So in other words, this is the omega-1 gap. So I looked at this and I started to analyze the Hausdorff gap from the same way you would analyze Einstein trees, and you will get actually a much more complex situation. So I thought maybe we should first study the descriptive version of this, and to now there are no Hausdorff phenomena there. In other words, there are no two orthogonal sigma-directed analytic sets. You can always separate them. As a matter of fact, you have this is the corollary of two analytic gap theorems for two gaps, dichotomies actually, which we are going to say in the more general form. But even these two dichotomies had some very interesting applications. Just this little progress there will give you solving a metrization problem in a certain class of spaces. There's a three-element basis for a compact set represented by class 1 functions. That this number p is very interesting. The space p is a poles example. You take the contour tree, points of the tree is isolated, branches are limits of these points in natural senses. So this is a locally compact space. You compactify. That's representable inside the bare class 1 function. It has this point in infinity, very complicated, meaning a very high character. This is why it's not metrizable. I will tell so. And it turned out actually this is the canonical object that every non-G delta point contains a copy of this with this x playing the point of infinity. This is followed from this gap theorem, and there was a beautiful application of this, which we used to solve the dual version of the famous separable quotient problem. It's the solution of a separable quotient problem for a dual spaces. Follow not so hard from this gap theorem. Okay, so this is the typical application. There's a notion of a definable that shows up naturally. You see, even in a dual space, it shows up naturally. Okay. And now we go to the general theory, which was developed in a series of papers with Antonio Aviles. Okay, so there's that if these pieces exhaust the spaces, we call it a dense, as well usually. And there's that ordering. We'll have to spend a little bit of time try to understand this ordering. So there is a map that maps piece into piece, and orthogonal of a piece to orthogonal of a piece. And it's mapped from the index set, maps index set. It's not like in the Tukey where you're mapping the sets, but the index set. It's kind of an analog of the Rudin-Kistler. And there's equivalence. Of course, this is a quasi-ordering, this is equivalence. And in the case of the n gap, which is the most interesting case, you actually have you don't need to look at the separate orthogonals, but there's the global orthogonals. There are various, for example, n gaps. If you close it downwards, then you see the n gaps are closed upwards. So in other words, in your classification, if there's a minimal, if you are going to find a basis, it's going to be a collection of minimal elements. Some of them are going to be n gaps, some are n star gaps, some are. And here is something that I want to point out: connection with topology. When you're doing this a double orthogonal, you're taking the interior of closure, so a regular open set. And this is typically coanalytic. But it hides no more information as far as the gap structure is concerned. I mean, it causes you there's no advantage of going into the coanalytic version. You see, so what I want to say is that the way you push through these gaps is this: you're pushing the regular open set to a regular open set in your trace. Remember, the regular open set is uniquely determined by its trace to a dense set. So you're not losing any information, which means that the gap gamma is isomorphic to a restriction of delta. Really isomorphic to a restriction of delta. So this is a very natural one, actually, very natural reduction. Yes, okay. There are also variants between this, but okay, this is the. Anyway, so we are interested in a minimal analytic if it is minimal in this order. And we are interested to prove this theorem, to see what is behind. I wanted to put this theorem, of course, it's another place where the basis problem is solved, but I want to put it from the point of view of expansion. I would like to point out what is the expansion you need to analyze to prove such results, and that expansion that could be useful in many other cases. You remember the case of the Levers expansion that were actually solving a problem even for a random graph, not just for rationals, original intention. So hoping to have seen thing here. Okay, so there's a very tedious classification problem. So this is something where you really get stuck. Like a 5, this and this is a 161 in dimension 3, etc., etc. So it's really very tedious to enumerate them. I'll give you some, but here is one result that is rather surprising. So you have a infinite family of pairwise disjoint open subs through beta n minus n. Each of them descriptive will give you analytic, actually reasonable. The point is that there are infinitely many pairwise disjoint. You take arbitrary 3 of them and assume that they have a point in the boundary, common point in all boundaries. Then you can find another point that minimizes, that avoids as many as possible. And 61 is the best possible. In other words, you can always avoid everybody else except 61. This is the, so you can solve by basically looking at the gap structure or generated by this. So you're splitting these into various gap structure. Okay. Okay, and now we're interested. Yes? Sorry? J is this 61, this number that corresponds to 3.
What is the other J?
Sorry?
What's the definition of J?
No definition. It's simply J is this best. The J of a, if I tell you that J of a 3 is 61, then you have a definition of a J, right? Is the for a minimal number, which is so that this statement is true for this number.
Does it correspond to the number?
And also it corresponds to the pieces of the number for gaps in a given dimension. There is, of course, there is even a formula for J. I did not prepare for a slide because I think why we want to. But there is a formula, and it's actually not complicated. But it takes probably one part of this whole slide there with lots of binomials or whatever. Yeah. Okay. The important thing is I want to point out that actually you can take a topological interpretation of this. And now that's the reason why I'm actually putting this, exactly because I'm interested in this expansion, which I think should have more application because of what I'm hearing from people. Okay, you have this uniformly finitely branching tree, n to the less than omega. And now there's a notion of a I chain, and I chain in the usual tree without square bracket is simply a chain where the two immediate successor, the next extends the digit I, immediate successor S, I. You see, the first statement will be just an I chain. But if you're required that you're not allowed to go above I, when you're moving from S to T, then you are square bracket I chain. So you see, so a chain has this type I if immediate successor of S, the ith immediate successor of S is extended by T for whatever you are, when every two S and T, or in particular two consecutive doesn't. When I put a two consecutive, that's okay. That's the I chain. And this is the gap. This is the gap theorem that I proved in '86 for n equal 2, but in this language. And so what is interesting here is so that somehow you are embedding, you are saying that for any analytic gap, there is inside, it should be mentioned that these I gaps do form that these collection of these I chains for different I's do form a gap. It's a downwards, these are pre-ideals, right? Close the monotone families, yes, and they form a gap is not difficult to see. What is interesting about this is that is this permutation. You cannot embed square bracket I into gamma I, but you must do permutation. And it's interesting because these are not strong gaps, which means that for example, some of the gamma I might be rather weak in information, might be countable, for example. Remember, in the power set omega modulo fin, you can always split two countable families. Two countable families will never form a gap. And one of them might be countable. And this permutation finds one. And if it is gap, there should not be other. So in other words, there's epsilon is some sort of measure of a strength of these pieces. Okay, so there is that W is for a word, but it's really a subtree of that. You can think of it as a subtree. So these are the pieces of your tree where the first digit is k, and the other is not more than a k. This is exactly the forced by your condition of I square bracket chain. And there is that now we are coming to the remember in any theory, in any Ramsey-Todorčević theorem for trees, you need to have a saying which sort of what is the closure, what is the expanded structure, which means the expansion. Of course, remember in the original for labor case, expansion is a tree, and you have to worry about the meets, various passing degrees, and various somehow notion which a strong tree can capture it. This is something quite different here. So the closure here, of course, has to be also meet closure, not surprising, but it's also closed under this walk from a lower node to a higher node. Lower node T, higher node S. You are walking and not passing degree. And I1, I2 are places where the digit gets increased. You take a digit, you go for a long time below it or above up, and then you change. Of course, fortunately, you can have only finitely many changes. And that's I always say fortunately, because typically you might have a theorem, Ramsey theorem, which is useless because the envelopes are too large. There are no bound on the envelopes. And here, fortunately, there is. Okay, it's set generated by. Sorry?
F is probably a finite set, right? On the previous set.
No, arbitrary set.
Arbitrary.
Yeah.
But if you start with finite, then it doesn't stay finite.
No. Closed. It's closed under the. No, it's no. It could be also finite.
They're finite.
Yeah. Well, downwards. I guess you take it downwards. Yes.
Okay.
Yeah. But the point is that again, you take in the old-fashioned mid closure, etc. But now there's a more closure point. There's a point where you're going from one node to other, and you're passing these places. You must push them all. Because the point is that these I chains can recognize them. The point is they know it. They know these places. Okay, so, and here is the equivalence. This is the correspond to the embedding type in the classical theory. Equivalency, or this is equivalence relation, right? Saying that you must preserve whatever you. Lexicographical ordering is this tilde, this, and also you must preserve. You must keep track when you are changing the digits, when you're increasing digits. I was warned about that. And now, so now it's how we are going to code an arbitrary set. We never want to code them with words. So now the sequence is, so you see it's fast because when you concatenate any, if you find a word in the semigroup closure of this, the word will know from where it's coming from. You can go back. So that's the idea here. Okay, so this is the, and now there's a, so you see again, it looks like we are in the category of Hell-Jewett theorem, but actually not. We are in the category of Hell-Jewett Gowers. You also shrink, you're allowed to shrink the digits uniformly by one. And the basic embedding has to preserve this shrinkage. I draw you a picture so that you can actually see what the basic embedding is. So basic embedding is like a strong embedding of trees, like a strong subtree. Image of a strong subtree, this is a strong embedding, if you remember. And this is the, this keeps the equivalence, so there's nothing strange happening. A basic subtree is the image of the original tree inside. Yes, yeah. And x0 set is simply equivalent to x. And this is the picture of a strong analog of a strong subtree of height 3. Remember on the first lecture, I gave you a picture of the strong trio high 3. Here, they are skewed. They should be actually skewed, spread even more, but there's no space on that. And you see that the passing, so in other words, these dots are the nodes in your subtree. The outside thing in the old theory outside, the moving from one dot to the next is completely free. You can do whatever you want. And here you cannot do, you must, you cannot go above the digit that you split. It has to be less or equal 1, less or equal 2, etc. So this is the new, and this is the theorem there. This is the, for every reasonable coloring. As a matter of fact, there is a characterization. You know, it's mostly measurable, C measurable, whatever, Borel or analytic, whatever. So in other words, if you have a type of a finite or infinite set, then for every partition of a subset that is isomorphic to it, in a Borel or analytic or array, there is an embedding of a basic tree. There's an image of this whole tree, so that all subsets are the same piece of partition. The space is there actually a topological Ramsey space, which means that is actually we have a characterization of the partitions for which this is true, not just a consequence. What is interesting here, that this is not a classical one. This is the ultra Ramsey space, which means the space of the U trees. So in other words, those people who know forcing, this is the space, this is the prickly forcing. Yeah. But it's interesting when you will say, well, look like you are using highly axiom of choice here. And I say, no, not really. You don't have a nice space, but you're not using axiom of choice. But nevertheless, it will be very interesting to actually build a definable Ramsey space. And here there is a problem more serious. And what the problem is the following. What we have here is the exact analog of the Millikan theorem, but we do not have a hyperweighted theorem. So we do not have a product theorem, but we have a homogeneous version. So it will be interesting to see. And this is the finite form, okay. Well. Okay, so let us now change the, unless there's a question about the previous thing, we change the, I just want to remind you this was done by hyperweighted theorem and this expansion by well-ordering rationals. You get this tree, you get all the theorem there, and you get this. And I should perhaps, there's an important problem to do the same thing for any other kind of homogeneous structure, at least I have a characterization. And there's ongoing work, and the progress is small, but still something that is interesting. And it does change. If you look at the progress that has been done, the expansion seems to be the corresponding expansion problem tend to generate the new Ramsey theorem about trees. It's interesting. Okay, we go now to topology. So topological version for a Q. Okay, so this is the, you want to now look at the expansion problem. You want to, again, what is the expansion problem for top Q? You look at the Q as a topological space. There is this, what is this two? You can either look at the two-element subsets of the Viatori space with this topology, or you can observe that the usual order rational is continuous. So you can take pairs so that the first one is smaller than the second. So it's a subset of the score. It's a little bit more easier this way because because remember, our expansion problem is saying you want to characterize all relations of all arities. And this is telling you that you will not be able to do that. He said, no way you can do that. Because in other words, you will not be able to find a finite expansion that catches you all relations. There's no finite expansion which is going to canonize all relations, obviously, right? Because you can always come up with one more from this list of preimages. In other words, you will not be even able to canonize binary relations, not just, okay. We'll come to this again. I analyzed in depth of this because as I mentioned last time that there should be a basis problem with the infinite basis, and I gave you some example. And this could be one. This could be one where and I examined the Baumgartner's example, and it did not quite look canonical. There's another one, oscillation map, that's finer than that, which is finer. Remember, if you want to canonize, if you are believing that you have something, that you should not be able to get anything finer than that. If you have no finer equivalence relation, should be possible to find. And oscillation is the natural one. So two sets oscillate, you throw out the symmetric difference and look how many times they intertwine. It's a very natural. Mapping is and it has this property that it takes all colors, not just on a copy of the rationals. It could take all colors on a discrete set. What is important when you take its closure? If its closure is large, then you're going to get the colors. That's something, and one of the reasons why I believe that there might be a classification here, because when you start playing with this with a higher dimensional Hyman theorem, it's telling you that this seems to be the best. This is to be high dimensional Hyman theorem tends to canonize relations modulo this. The only, it can canonize up to, unfortunately not up to the all, our mechanization is coming up to the full copy of the rationals. If you want to a sufficiently large number of counterbending derivative, then this is correct. Hyman theorem will give you that. In other words, you will not be able to split this modulo that. Okay, continuous version. I examine also continuous version. This oscillation map is not continuous. Of course, if I'm not continuous on countable space, then you know what's the next complexity, because it's always F sigma or G delta, whatever you want. So the lowest complexity, this is the, so here, what I want to say, there's no analog, definable analog here correspond to continuous. There's no Borel. It's meaningless to ask for a Borel, because it is Borel. And continuous turned to be actually true, and and the proof uses Hyman theorem in higher dimensions. As a matter of fact, uses Hyman theorem exactly in dimension 2. And if you go to dimension 3, there is bad news. There's a continuous coloring. In other words, there's a continuous coloring which is actually again has a similar. This on a large number of counterbending derivative, you take those colors up to that. So it goes slower than 2K. Something I must say, when I was preparing this, I could not find the formula for how it takes color. How many counterbending derivatives you need to catch some colors, but okay. So in continuous version, but interestingly, if you want to, again, go to the Erdős-Rado analog, you want to equivalence relations, you can classify them. Remember, recall that Erdős-Rado theorem, canonical theorem, requires of dimension D requires a 2D Ramsey theorem, 2 dimensions up, twice the dimension up. Here, actually, we do not have a Ramsey theorem for dimension 4. Yeah, not even 3, but still you can classify them. It's an interesting situation. There is a classification for this.
So the second theorem here, you do have this analog with when you count counterbendings on the derivative.
Yes, exactly. It's not 2k, as I said in the previous, not 2 times k. You take the colors all the way up to 2k. If you have a k many derivatives in the closure, you take the first 2k color. It's not 2k, but some maybe I think log k, or I forgot exactly what. But its function goes to infinity. So therefore, you get this, that you take all colors. It's actually very natural. I mean, I cannot tell you what it is. You take 3 sets. They have a general position in a tree. Look at the 2 sets which split from each other longest. You cut. There you get 2 sets, oscillating these 2 sets. So we see a picture. You have 3 sets. You can think about this is the intersection is a fragment of both, if you like. You cut the place there. You need to cut it to be continuous. If you don't cut, it's not continuous. You need to know, and now you oscillate, you see how many times these 2 sets intertwine. That's the function. It's a very natural function, actually. Okay, there's that well-known, again, we always, no matter what we do, we go back to Sierpinski. Why is that? Because we go back to well-ordering, right? He simply said, well, there's a well-ordering, and you have to deal with it. And you have to deal with it. Except if you look at the R as space, topological space, there's distance. And just to avoid a problem with the connected, etc., let's assume that our copy of reals is a counter set, actually. But you have ordering of the counter set, and you have usual Kafka ordering, which is continuous, so it's really not a, but it's good to have it because you want to canonize relations. So you have to mean the relation tells you which, when this is true. So Sierpinski expansion is natural for us to consider, because remember, how do you solve expansion problems? Because expansion problem is a classification problem of all counterexamples. You're trying to get all counterexample, not just one. He got one, so you're hoping this is all. That's essentially what it is. There's not much of a more philosophy of that. You know, somebody get a counterexample and you want to say, well, this is it. There's perhaps no more. And let's see how far is this from truth in this case. So what I want to point out this particular property of Sierpinski, which is obvious from his proof, etc., that he realized all these colors, k factorial, k minus factorial, on any, not only on any, he proved it every uncountable set, but it's actually only set which is dense in itself. Copy of rationals, right? Of course, he did not point it out this in his paper because he did not think about today's, you don't have view. Okay, so Galvin actually in a series of correspondence with lots of people, I'm sure lots of people, including Richard Lever, was popularizing, even called it the Galvin conjecture. And in fact, even in one of the places, he was even, he of course noticed that this contradicts continuum hypothesis, but he was hoping that the continuum can be Aleph 2, that this conjecture doesn't rule. What the S-canonical means, basically every relation can be described using these relations there: metric, well-ordering, and the usual ordering. And this is actually in K equal 2 consistent. Unfortunately, with a very large continuum. Very large continuum, so it's not... And now let us look at the cardinals show up. This is the length of the well-orderings, naturally, so it's not surprising. So this must show up. So this usual, this is another oscillation mapping. This is oscillation mappings on a very higher. So what he originally thought is actually not correct. Continuum has to be large. So Schlag attempt somehow necessary to continuum has to be large. And now this is a very natural question: is this the place where we stop, or there is something more? maybe there's another series of mappings that pushes this up. Whichever is true, I think going to be interesting. Okay, let us look at the Borel combinatorics version. This is again very interesting. So again, now you are forgetting the ordering. So there's no well ordering. And you have again the same structure. And you have a conversation theorem. This is first, of course, tried by Galvin in the up to dimension 3, I think. Higher dimension dependent on Topological theorem. Interestingly, Blas was using Topological theorem, not Millikan, although this is rather immediate consequence of Millikan's theorem. Okay, so you can, in other words, this solves the meaning that if you're interested in just partition of this symmetric, could you have a k minus 1 class because this is the relationship, this is this other factor of the Sierpinski, just the relationship between the distances. And there's nothing else going on. Okay, I guess k equal 2, this is 1, so we have actually a constant value, which is actually what Galvin observed. And there is a possibility to classify all these. You see, these are finitely, so these are the previous was with the finitely many classes. So you try to go to the level of Erdős-Rado. And this happened to be actually very tedious, although I think is a very interesting project. Lots of people worked. This is the list from the last paper of Litas. Lots of previous attempts. Okay, so Taylor was the first, gave the first equivalence relations with counter many classes. There are two, which are two, right? With a counter many equivalence classes, either trivial one or a equivalence relation given by a distance. And this other, if you go a little bit, if you look at dimension 2, then you don't have too many, and the dimension higher you can annul it, but it's becoming. I wish this list is more clear. That the invariants could be made more clear. Because when I prepared this talk, I tried to find out. People tend to give me invariants, but they don't offer a way to compute them. So I have to do by hand. I think there should be a very reasonable formula there. Okay, let us now go to the arrow notation. This is a very elegant notation that somehow avoids a lot of writing or notation or quantification switches, etc. So let us go to this. By the way, this binomial notation is in Skolem. I was thinking who first invented it, and there are lots of people which were. I thought the first place, earlier place I looked at this was in Skolem's paper, in that Skolem, the first one. He think about them as a combinations. So it's simply a substructures isomorphic. You can also think in terms of embedding, but let us not do it for the moment. It's not, because not that. Okay, so there's the standard notation. If you color with lambda many color, you can shrink it down to tau colors. And there's that square bracket notation. This is interesting. This was invented by Erdős, Heinel, and Rado in '60s, purely as on a theoretical ground for cardinals. Somehow it's interesting. They found it, and this is what I found in letters. Tried to prove or disprove this reformulation of a Lever and Devlin. So this is, you see, they come in pairs. They come in pairs, saying this is the minimal. Okay, this is the conjecture of Sierpinski-Galvin. There is a example of Sierpinski and conjecture by Galvin. Okay. You can state this in this way. They're interesting Galvin-Schlag. This is the example very much close related to the Dushing-Miller example to this Raizé or the linear orderings. Some say uses the similar technology, but interesting when I look at this example, I noticed that this is really follow from the you can find a continuous coloring with this. There's a continuous coloring this on a very strange subset of reals. So the complexity there is not the way you assign the color, but where you restrict the set. This is the thing which I already mentioned you. This is I mentioned this because there was a very nice work analog of the Lever-Devlin for the random graph, but what they had would give you a Ramsey degree of the complete graph. You know, these so-called Devlin types are giving you Ramsey degree of complete subgraph of the random graph. So in other words, you don't have more complexity if you're looking at the complete subgraph, but you have a considerably more complexity for arbitrary graph, even for paths. Even for paths is very difficult to see what is the Ramsey degree there. Okay, so I also made a more recent thing with Dilip. There's again coming in pair. There is a Sierpinski thing, and there is that positive one, which actually we use large kernels, which is much more general than not just for reals, for actually any non-sigma discrete metric space, any non-trivial space. Actually, characterization space where this is true. So let us examine this a little bit, because it's this is a two-dimensional version, and we'll like to see for three-dimensional what's happening. It turned out that the three-dimensional version has something to do with the kernality. So if you look at the k equal Aleph 0, this is exactly Baumgartner's theorem. K equals 0, this is a two-dimensional, x is countable. So you have this, if you have a positive dimension k, the reals must be of that kernality. So if you want to see what is dimension 3, this is this. If a Sierpinski expansion is correct, meaning that 3 factorials times 2 factorials is the Ramsey number, then there continues at least Aleph 2. So it's a very interesting situation what's going to happen here. You see, every time, whatever you are doing, whatever you're proving, you must be inventing technology for a positive result. You must be inventing a way to realize it. You must be, or show that Sierpinski expansion is not the right one. Yeah, that's another way. Yeah. Okay, so now we go to the beginning. I started with this, and I come back to this, and I want to examine it from this arrow notation, because remember what was on the first talk situation. Then you see over the shoulder of these people which are doing structural Ramsey theory. You formulate it in the way that connection with dynamics is obvious. Become obvious, but now you like to like to understand it in the to see what is the where you can change, which sort of a structure you need, what is the condition. So you need this sort of a notion of Ramsey number, which actually showed up in the previous, only not in a structural form, but in a topological form or a kernality form, but it is a structural form. It's the minimal number for which this is true. So minimal number for which this is true, when you write this, if it exists, it comes with the two things. First, that if you take the limit, Freisel limit of this Freisel limit, there is a counterexample. that you, in other words, there is a square bracket version of this in this some number that cannot be some number T of A. So that what, in other words, we are very much interested in this example, very much interested in this example, because this example is going to give us a representation. Otherwise, infinity, Ramsey degree, etc. This is Ramsey class if it is a one, all standard. And it's very convenient to write this in terms of the limits, not to have a C to be finite. So this is the one of the consequences of Nash-Rottle, but it's much easier to see. It's perhaps much easier to see it using finite union theorem, some kind of a Hyman theorem. You don't need pairwise construction for that. Okay, so that's the way. This is what they do. You fix your class age of this. You take you expand it, and now for a purpose of just saying how things. Let us assume that it is a finite expansion. It's a finite expansion. And then this is what you really should be looking at. You have this finite expansion. You can also assume that it's also Friese, jointly or Friese. And you look at what a tomorphism group does to it. Moves it around this. The thing is here, I want to point out that it is actually obviously a finite number. Of course, it may be completely irrelevant for you because this number is simply you just expanded and you are hoping that this is going to do something for you. It's a finite. This is good sign. But that's the promising thing. If you prove that this expansion has the Ramsey property, this is what the people do. Then this gives you upper bound on the actual degree. So this number is a natural upper bound. So this is finite. That's what we're interested in. And so this is the expansion property is ordering property that I mentioned you last time. Simply that you can always find that embedding, no matter how you expand it. Very natural. I mean, essentially, saying you like to see that all you have a guess for this coloring. You like to see that all classes are realized. You really want to witness this relation. That every copy of B uses all classes. So this is this. Every copy of B, the copies of A inside B uses all the colors. So you get a equality if you have both Ramsey property, expansion property. So a very simple calculus there. And if you want to do reverse, you have to actually, interestingly, you have to a little bit. You're not allowed to use finite many relations. You must allow infinitely many, possibly infinitely. The reason is kind of a simple. You see, suppose you get this for every A, you have infinitely many A's. So I told you that whatever you are doing, you must be taking into account these examples, these partitions. So we are introducing for each A one relation. Or finite for each A finite many relation, but there are infinite many A's. So we are really introducing infinite many relations. So the relations that I have in mind to examine simply are pieces of these colorings. And the pre-compact, what I said is when you're restricted to edge, is still finite. It's simply this number is finite. Let me just say what that number is. That number there. So basically the automorphism group cannot, if you take your finite structure A, you move it back. You look at how many types you are realizing in the expanded structure, this has to be finite. Even though, remember, expanded structure has infinite many relations, so you must be, potentially you might be seeing a mess there, lots of infinite, but actually here he's saying that actually you're not going to see. That's the definition of precompact. And the point of, and you have a reverse. So in other words, in this case, you can put this and you catch this. And there's an interesting proposition here which comes from a topological dynamics. Application of topological dynamics to Ramsey is one of the first one that was found. So in other words, you really don't need to worry about expansion property, really. You need to, well, you have to be careful here when you say you need to worry, because remember, this is a classification problem. So existence of the classification doesn't really solve the classification problem. You need to know if you want to have a deeper application, you need to actually work with a given representation. So if you mean expansion problem, you have a solution. But another thing is, as I mentioned, there for Borel version for a perfect set, we know there is a finite, there is expansion problem solved, but you don't really know what the solution is. And here is the topological dynamics reformulation, which I mentioned you last time for a random graph. So if you take a precompact expansion, this action on the space of all such is universal minimal flow, if and only if this expansion has the Ramsey property expansion property. So you are capturing the finite Ramsey. If you have a finite Ramsey degree, you have a universal minimal flow of that sort. One of the things which is interesting here that this universal minimal flow is metrizable. And in a beautiful paper by Andy Zucker, he reversed that. It's actually a finiteness of the Ramsey degree follow from the fact that this universal minimal flow is metrizable. So in other words, what is written there is if and only if, meaning that, in other words, the expansion problem for the Freiset structure F is equivalent to the metrization problem. So it's I wanted to point out this, that sometimes these expansion problems can be thought as some sort of a general metrization problem, versions of metrization problems. This is one of the very interesting cases. And I'm close to end, so I like to do the references. Yesterday I forgot to put you this reference because I was not, which I did in the slides of yesterday, which I put on the web page of the institute. So they are going to have references for the previous talk, and here the one that are on here. The reference where you can find more things. So thank you very much.